The buffer overflow, the infamous hacking concept that has been plaguing the cybersecurity community since its inception. Attacks leveraging buffer overflows have been the cause of thousands of hacks, leading to the theft of personal information by cybercriminals that is eventually sold on the dark web. But how do buffer overflows work? Why have computers historically been so prone to buffer overflows? And how does a buffer overflow give a hacker access to your computer, and is there any way to stop them? So what is a buffer overflow? As the name implies, a buffer overflow is when a buffer of memory is allocated for a particular data type. Something in the logic of the program goes wrong and more memory fills the buffer than the buffer has room for. Hence, it is overflowed. One of the most commonly seen buffer overflows originates from how strings are stored in C. A string in C, like this one, is just an array of ASCII characters, and we can create a string with this line of code. When we go to print it, the string prints out and everything works out just fine. But how does a program know when to stop printing? Why doesn't it just print all of the data after the string too? This is where things in C start to get a little weird. You would think the answer is, well, obviously the length of the string is encoded near the string, so printf just reads that number as the length. Well, that's actually not the case. Remember how I said that strings are just an array of ASCII characters? Well, yeah, that's all they are. The only way functions know that they've reached the end of a string is if they hit a special character called the null byte. If they don't hit that null byte, they'll just keep going. Unfortunately, strings that just keep going apply not only to displaying information, but also getting information from the user. This is where the hacking begins. A well-known vulnerable function, getS, does just this. It just keeps going. In this code here, when I create a buffer for a 64-byte string and use getS to get a string from the user, at first, everything seems fine. If I give the program more than 64 bytes, this is where things start to get a little weird. Because getS doesn't know the length of my buffer or the length of the input string, getS will read more than 64 bytes. Eventually, after 70 or so bytes, my program begins to behave non-deterministically and eventually crashes. getS is so dangerous that even the man page entry for getS says getS is dangerous and it should not be used. But who cares? How can data leaving a buffer give a hacker control of my computer? Hackers can abuse the buffer overflow by taking advantage of how functions call each other. Here I have some code. Function main calls function add. On the right I have a diagram depicting memory in the program. The structure is referred to as the stack. When add gets called by main, a few things happen. First, the arguments to add get pushed onto the top of the stack. That's the numbers x and y. Add will use these later as arguments into its function. After that, the processor needs to remember where in main to go after add returns. This is referred to as the return address, which is also pushed onto the top of the stack. Once all of the data is put on top of the stack, add gets ran, and add makes room for its local variables above all that other data. Add runs, and eventually the program returns into main where the function got called. Do you see the problem? If the called function add has a buffer overflow in it, the return address into main can get overwritten, pointing to code that wasn't originally supposed to get ran. Let's look at a different program. This is a secure server. Well, not really, but to get into the server, it checks your password against a password that we can't see here in the code. If you get the password right, you get a shell on the server. Seems pretty simple. But look how we're checking the password. The first function that gets called is getS. Remember how the return address from main was put onto the stack? Well, now, if we overflow the password buffer, we can overwrite the return address and return directly to the debug function and get a shell without knowing the password. Our server has just been hacked. That's pretty cool. But if we just stopped using getS, does the problem go away? No. The unbounded string vulnerability is actually found in a lot of other string operations in C, including strcpy, scanf, sprintf, among a bunch of other functions. Now, don't let this stuff scare you. Computer security has come a long way over the last 20 years, with mitigations that make most of this code really safe, even with the use of these dirty functions. But those mitigations would take an entire other video to discuss. When you're coding, code defensively. Don't trust the input of the user at all. Assume they'll never play by the rules and set limits on how much data they're allowed to give you with n variants of functions like stir ncopy and snprintf. Or if you want to try hacking in a legal, ethical way, go play a capture the flag or CTF. Here I'll show you picoctf, one of my favorites. CTFs are a great way to be exposed to code vulnerabilities not only for the hacking's sake, but also so that you can make your code more defensive. Before you start hacking away, leave a like and then go watch this video on how these 14 characters will crash your computer.